Here's another question that's quite familiar from anyone who's looked at AP papers. A car leaves an intersection traveling north at 50 miles per hour, and that's this one here, and that's the first car. And another is driving west towards the intersection at 40 miles per hour, that's car 2. At a particular instant, the northbound car is 0.3 miles north of the intersection, while the westbound car is 0.4 miles east of the intersection. Well, those things are changing, so we won't put them in yet. But at that moment, how quickly is the distance between the cars changing? How quickly is the angle theta, as shown below, changing? Well, as we look at this, and any time you're given directions, cardinal directions, and you're talking about north, east, south, and west, you're talking about right angles. And hopefully everyone can appreciate that there's a right angle here. And we were asked for the distance between the two cars, so we better label that, and that's this distance in brown here, so let's call it S. S is the distance between the two cars. And then the other quantities that we'll need to measure are the distance that car 2 is away from the intersection, and the distance that car 1 is away from the intersection. Now the temptation is to label these as 0.3 and 0.4, but they are changing all the time. So we can't actually write down 0.3 and 0.4. You have to label them as X and Y. Okay, now along the horizontal, that's normally what we call the X-axis, so we might as well label that as X and then label this as Y. But let's carefully define each of these variables here now. This is something hopefully after having done the last 3 examples you realize the importance of. So let X be the distance, I guess it's strictly speaking the displacement, of car 2 from the intersection. And let Y then be the distance of car 1 from the intersection. Okay. Let S be the distance between the two cars. And I suppose for completion we should define theta, but rather than go into some long wordy explanation of what theta is, let's just write down let theta be the angle indicated in the diagram. Okay. Well, let's look and see what we're given here and what we are required to find. So a car leaves an intersection traveling north at 50 miles per hour. So in other words, this car 1 is traveling north away from the intersection. In other words, its distance from the intersection is increasing at a speed of 50 miles per hour. Now, that seems fairly innocuous, but it's actually a big statement, because for the first time, maybe this year, we've said that speed, the speed of this car traveling north, is actually now a rate of change of distance. Okay? Said the distance that car 1 is away from the intersection is changing by 50 miles every hour. So that's the rate of change of position. So in other words, speed is the rate of change of position. And that's a general thing that I want you to take from this example and to hold on to. So the given rates, dy dx, dy dt, we have to be very careful here. Dy dt, I have to be very careful. We said it's increasing because it's traveling away from the intersection at 50 miles per hour. So that distance, y, is increasing at 50 miles per hour. The other car is driving west towards the intersection at 40 miles per hour. So if you look at the diagram, if you're traveling towards the intersection, you see this distance x is getting smaller. So dx dt will actually be negative 40 miles per hour. Okay, dx dt is equal to negative 40 miles per hour. And what are we asked to find? Well, in question 1, we're asked to find the distance, the rate at which the distance between the cars is changing. Now, the distance between the cars is s. The rate at which that is changing is ds dt. So the desired rate well, in question 1, it's ds dt. And in question 2, if you were to go back up here again, is how quickly the angle is changing. So we'll say that's d theta dt. Now we'll do one of these at a time. Let's start with 1. Okay, so we're looking for ds dt. So you want an equation that relates s and y and x. Okay, and hopefully you can see looking at it that that's a right angle triangle, so Pythagorean theorem applies. And the Pythagorean theorem, remember, is s squared is equal to x squared plus y squared. Okay, differentiate everything here with respect to t. Now, differentiating with respect to t means you're going to have to stick on d dt at the end of each derivative. So the derivative of s squared is 2s ds dt is equal to 2x dx dt plus 2y dy dt. Now, we're told that at the instant we're involved in looking at the northbound car, in other words car 1, is 0.3 miles north of the intersection, so y will be 0.3 and x will be 0.4. So y is 0.3 and x is equal to 0.4. We can only put these things in after we've differentiated. But it still leaves us with a question. We know dx dt and dy dt. We can write those down as well. We have those. dy dt is 50. You can see here at the top of the screen dy dt is 50. dx dt is negative 40. So we know those as well. We want ds dt. The bit that we don't know is s. Now, in this case, we're looking at a static situation. Okay, we're looking at a static situation. And so we can draw a static diagram. We've already done our differentiation, so we're allowed to do it like this. X is 0.4, y is 0.3, and at that instant, if this is a right angle triangle, use Pythagoras' theorem. It's a right angle triangle, it's a Pythagorean triple, 3, 4, 5. So this will be 0.3, 0.4, and 0.5. Now if you want to, you can work that out as s squared equals 0.4 squared plus 0.3 squared. And you'll find that s is equal to 0.5. But if you know your Pythagorean triples, 3, 4, 5, divide each of them by 10, that tells you what s is. So we are now going to start filling this in. Sorry, it's bouncing about on me a little bit, but 2s. Okay, that's going to be 2 times 0.5 by ds dt is equal to 2 times x was, if I can make this work, 0.4, and dx dt was negative 40, plus 2 y is 2 times 0.3, and dy dt was 50. Okay, so let me go back and correct just something here. This should have been 2y dy dt. Not sure what happened there. Okay, so it's pretty straightforward from here. 2 times 0.5 is 1, so you get ds dt is equal to 2 times 0.4 by 40. And what we have there, 2 by 0.4 is 0.8. 0.8 by 40 is it 3.2? Or negative 32 actually. Negative 32 plus 30, which is equal to negative 2. Now, s was a distance. Be careful of your units here. S was a distance, and all the distances were given in terms of miles. So it'll be miles per, and time was in speed, measured in hours, so it's -2 miles per hour. In other words, the distance between the cars is decreasing. Between the cars is decreasing by 2 miles per hour at that instant. Now remember, the derivative only applies at a particular moment in time. And please don't say moment in time like I did. But there is that first question. Okay, now if we want to look at the second part of this problem, which was to think about the angles that are involved. Okay, so part 2, the angle. So again, our situation is as shown. This is theta, this is y, this is x, and this is s. Well, you can go with any of the trig functions. So let's say we go with sine of theta. Okay, sine of theta would be the opposite, which is y, over the hypotenuse, which is s. Okay, so let's differentiate. And differentiate sine of theta, you get cosine of theta. Now you're differentiating with respect to time, so d theta dt is equal to, we've got to use the quotient rule here, so it's the bottom, s, by the derivative of the top, dy dt, minus the top, y, by ds dt, all over s squared. Now, we're going to start plugging things in. At the precise moment that we're interested in, cosine of theta, remember 0.3, 0.4, and 0.5 was the static diagram. Okay, so theta, 0.3, 0.4, and 0.5. Cosine there would be adjacent 0.4 over 0.5 by d theta dt, which is what we're trying to find, is equal to s. That distance between them was 0.5 times dy dt was 50 minus y is 0.3 and ds dt was -2. We just found that out a few moments ago, over 0.5 squared. Now, that will be, if you work that out, 4 over 5, and I'm running out of time here, so I'm probably going to skip a lot of the arithmetic and just give you the answer, because I've set it up already, is going to be 50 times 0.5 is 25, plus 2 by 0.3 is 0.6, divided by 0.25, and d theta dt will be equal to 5 times 25.6 divided by 4 times 0.25, which works out as 128. 128 radians per hour. Okay, so hopefully you can work through the arithmetic and confirm that that's correct. It takes quite a long time to do that problem, but again, it's a pretty standard AP exam problem. I hope you followed it. Sorry if it's gone too fast. Watch it back at your own pace. Okay, thank you.